Okay, we're back with another problem. This one is something that we've sort of discussed at one point or another. Um, but this problem deals with having a ball that is dropped from a certain height and then perhaps dropping something on top of it and looking at some interesting kinematics and momentum energy relationships resulting from this situation. Um, okay, so a ball of mass 9m is dropped from rest from a height h at 5 meters above the ground as shown on the left. We're dropping this ball 5 meters and we're falling with gravity of 10 meters per second squared. Air resistance is negligible and the collision process is almost instantaneous. Okay, so we want to determine the speed of the ball immediately before it hits the ground. Well, let's give ourselves a little bit of space here. So, assuming we drop right before we hit the ground, well, this is simply a conservation of energy problem where we are converting the potential energy of gravity into the kinetic energy at the bottom, which is 1/2 mv squared. So having the plugging in the values here, we have 9m times 10 times 5, and that's equal to 1/2 of 9m times v squared. The 9m's cancel. I'm left with 50 equals 1/2 v squared. So 100 equals v squared. So therefore 10 is v. And the unit is meters per second. So we're going to be going after 5 meters drop, 10 meters per second. Conservation of energy makes this slightly trivial. And I guess now we want to know the time after release of the clay blob at which the collision takes place. So we're looking at an elastic collision that occurs when the ball and the clay are at the same height. So we're looking at this situation here, and we're seeing that somewhere in this range, we have maybe some sort of collision. Now, if this were linear, which it's not, it's quadratic, but if it were linear, we'd expect that they'd meet in the middle. But that's not the case. Presumably, we're going to meet somewhere else. Now, will we meet in the middle time-wise? Will we meet in the middle height-wise? This is an interesting idea. Let's go a little further. So let's look at the time after release that the clay blob at which the collision will take place. So they occur when they're at the same height. Now where that height is, we don't know, but this collision is going to occur when they are both in the same place. So we know that the height of the ball is going to be related to its speed times time. It's essentially going to be an equation of this form. Y equals y0 plus v0t plus 1/2 at squared. And it turns out that because we have a negative 10 here, This is going to be minus. So what we end up getting is that we have whatever speed we start at off the ground minus the effect from gravity. So this is bringing this back to kinematics. And the equation for the height of the clay is going to be its initial height. We don't have initial speed there for the clay, but we do have initial height. Let's call it h, which we know is 5 meters. And that's going to be minus however much height we lose due to gravity. And because we see these equations that have this same time variable, and we should be able to know everything else. Well, we know the V0 here, it's 10. And we know that we don't know the time here, we know the time, we don't know the time here, we don't know the time here, but we know G and H in all cases. We can say that they're equal. We know that we have the heights, the locations have to be the same. So the height of the ball equals the height of the clay. So we get V0t minus 1/2 gt squared is equal to the height minus 1/2 gt squared. And, well, we have this term on this side, this term on this side, and they'll cancel each other out. And we have V0t is equal to h. Well, these are things that we know the values of. This is 5. This is 10. So let's think about what this means. Well, it turns out that t is equal to 0.5 seconds. So the time is indeed at 0.5 seconds. The height, we will see, is something that we are going to develop in the next question. Okay, so this is the time at which ball collides with clay when, and the condition that let us find this is when at the same height, because they're in the same place at that point. Let's move on. Determine the height above the ground where the collision takes place. So let's think about this. The height above the ground. Well, what should we do? We had expressions for the height right here. And we had the expressions for the height, so let's take the time value and just figure out what that is. So for the height of the clay, why not plug it in for that? Because the height of the clay is sort of an easy expression there. We have 5 minus 1/2 times 10 times 0.5 squared. So that is 5 minus 5 times 1/4, which is equal to 3.75 meters. Rounding up with 2 significant digits to 3.8 meters. It's 5 minus 5/4, which is equal to, that would be 15/4. So we find that we collide at this point at 3.8 meters above the ground, or 3.75 meters above the ground. And if I move forward on this, we have to determine the speed of the ball and the clay immediately before collision. Well, this is a little bit of more a little bit more kinematics. And oh man, tired. Well, the kinematics for speed are that my v maybe of the ball is equal to the initial speed of the ball minus the acceleration due to gravity times time. Well, my initial speed is 10 minus g, which is 10, times 0.5. Well, this is 5, so the VB is equal to 10 minus 5, which equals, let's fix that up, 5 meters per second. 5.0 to hit the significant digit mark. And the V of the clay is equal to the V0, which is just 0, minus 10t. Well, it turns out that this is the same thing. T is, let's undo that. T is 0.5. So this part of the expression is the same, and it's just going to be pointing downward. They're both going the same speed, just one is pointing up and one is pointing down. And we care about the speed, so they are just the same speed. And if you used 9.8, you'd find that this value is 4.9 instead. Notice also above here, you could have plugged into the other equation and found the height the same way. You just would have had to do a little more calculation. So finally, if the ball and the clay stick together upon impact, what's the magnitude and direction of their velocity immediately after impact? Well, you want to pay attention to the fact that this has mass m. And if that has mass m and this has mass 9m, well, the momenta are going to be slightly different. And this is going to be a momentum problem. We're going to say that we have a momentum before of 9m times v up, which is 5, and then that's going to be added to the momentum of the other object going down, m times minus 5. And then that's going to equal the combined mass times the VF, which is the thing we care about finding. Well, let's try to figure this out a little bit. Well, if I plug these values in, I'll find that I have let's try to do this sort of algebraically really quickly. Okay, so to find the VF, all I have to do is divide by this value. So I have 9m times 5 plus m times negative 5 divided by 10m, which is that value, and that equals VF. So if both of these have m and this has m, I can just simply cancel those out, and I get 45 is equal, or 45 minus 5 over 10 equals VF. Well, this is just 40 over 10. A conservation of momentum leaves us with this relatively easy situation. So if this is obvious that this is up because you used a negative up here, that's great, but we do want to say that this is upward. The speed is upward because most of the momentum was with the upward pointing object before the collision. Okay, so this was another problem that is sort of useful to consider. There will be one more problem before we move on.